Okay, yeah. So basically, this will be just a simulator, also in quite similar ideas of Jacot in what we are proposing. It has been developed by me, Xavier Oriols, and Carlos Estefani and Xavier Cartuchat. We are planning to develop in the development 3 and the September 3, but we have already some preliminary results, and so you can get an idea of what we want to simulate. Yeah. So basically, what we want to simulate is this type of systems that is just one electron and light, only one mode, only one frequency in a cavity, and the interaction between the electron and the light. Yeah. This can be for a closed system, and we also are planning to do it for an open system. It says that instead of an infinite well, we are using a resonant annealing diode with 2 barriers and also in a cavity. And this is the system that we are simulating. Okay, how we will simulate these systems? Basically, we will work with this type of Hamiltonian. This type of Hamiltonian, you see the kinetic energy and the potential energy of the electron. This is the kinetic potential energy of the photon. This is the interaction. This interaction is in the dipolar approximation, just for 1 degree of freedom that is the electron, another degree of freedom that is the light. Yeah, and we will have several ways of solving this problem. One will be with classical classical light. Basically, it means that you are using just the Hamilton-Jacobi equation to find these kind of trajectories and find what is the solution, or what are the results. We also will use a classical light and quantum electrons, where the electrons will have this behavior and with these commuting properties. So this will be the equation that you are solving is a wave function just with the degree of freedom of the electron, and this is just a parameter, the external parameter for the electron. And we will also do the classical electrons and quantum light. It means that now is the light that is quantized, it has these properties, and this is the wave function that you have, a wave function with the degree of freedom is the Q, that basically is the amplitude and the phase of the single mode that we are studying. And we will also use quantum electrons and quantum light. That basically means that both the electrons and photons satisfy this commuting relation. And this is the equation that we are solving. It basically is just a 2-dimensional equation that you can make some approximations and do it in a quite fast way to simulate. And we will also, in this quantum version, we will also add this computation of velocities. This computation of velocities that are typically Boolean velocities, but are also what it is known with values of the momentum of the electron, or with values of the momentum of the light. That is just some type of trajectory, understanding the trajectory as the amplitude of the electromagnetic field. Okay, so what will the students find? It will be just a program more or less like this, where they will choose which system they want to study, which type of simulation, classical, semi-classical, quantum, and then for each type of simulation, which parameters, with packets, everything, parameters that can be adjusted, what is the alpha that it provides interaction between the light and the electron, several parameters, and finally they will just make a run, and they will have some simulation of what is the results, and the idea is being user-friendly and very didactic for the students. And so what can be studied? One thing that can be studied is Rabi oscillation, where you see some interchange of probability between electrons and photon states. Also spontaneous emission. You can also try to discuss spontaneous emission with your classical models to see what happens. You can study simulated emission and absorption. You can study quantum transport with polaritonic natures, and you're going to study also these weak values of electrons and light. And I provide here sorry, what I have done. Yep, some example. This is just an example of the Rabi oscillation, and what you see here is this is the degree of freedom of the electromagnetic light. This is the degree of freedom of the electron, and what you see here is that it's changing from being basically in this indecision state to being in this second state, and here you see the same of being here in just the first ground state, that is the vacuum state, and in the first state, which is energy, and basically what you are seeing is just the Rabi oscillation between these states, and also you can provide these trajectories to explain basically the same phenomena, where you see here this one particular trajectories that are in the degree of freedom of the light and the degree of freedom of the electron, and these movements of the trajectories provides where in the gray shadow regions you have one photon, and in the white you have 0 photons, and you see dynamic transition between them when you see in time. Also, another example that you're going to study is just this electron transport in open systems, where these are the states of the resonant tunneling device. But when you put light and you have some frequency that is in resonance with the resonance of the electrons, you see some splitting of the energies. And then instead of having this transmission coefficient for your electrons, you see for your electrons see a transmission coefficient where you see some splitting of the energy that is just this splitting of the Zener states of the whole system, not of the Zener states of the electron or the light, Zener states of the whole systems. And so you see this some kind of Rabi oscillations, but in an open system. And this is basically our idea. These are just very preliminary results, and this is what we wanted to offer. And that's all.
Amazing, thank you so much. Shannon, do you have your hand up?
Yeah, if I could.
Yeah.
So yeah, I'd be very interested in this model. It looks quite interesting. I was thinking maybe there's a very good opportunity there to illustrate and maybe visualize concepts from second quantization of light matter interactions, for example, commutation relations, for example, photon correlations. Is that something you've thought about, going beyond, let's say, a wave function P chart to illustrate these more advanced?
If you say correlations and you want to put more degrees of freedom for then it can be a problem. It can be a problem, basically a numerical problem, because we are planning that even in a 2-dimensional degrees of freedom, we can support more or less fast simulations, so that the student will not spend a lot of time waiting for the simulation. But if we increase the complexity of the more electrons or more degrees of freedom for the light, then it will be a problem. But apart from this, we are open to whatever.
Something simple like single photon emission, for example.
Yeah, no, this of course, this is no problem, and this is just spontaneous emission, and this is no problem. And you understand in a very easy way. You understand the creation and annihilation of particles as a transition from the ground state of the harmonic oscillator to the first excited state in a very simple way. And even we have these trajectories that then you recover somehow a meaning of the properties of the electron, the properties of the photons of the electromagnetic field. So we are completely open to discuss with you, and we'll be very happy to go in the directions that are useful for you.
Okay, happy to talk. Thanks.